Electrical and Electronics Engineering. My today's concept video topic is Laplace and Poisson's equation. So, Laplace equation follows from Poisson equation in the region where there is no charge density. The solution of Laplace equation are called harmonic functions and has no local maximum or minimum. All extrema occurs at boundaries and hence correspond to smooth surface available. So, the electric scalar potential field we are defined in section is useful for a number of reasons, including the ability to conventionally compute potential differences, that is, V21 equal to VR2 minus VR1, and the ability to conveniently determine the electric field by taking the gradient, that is, E equal to minus grad of V. One way to obtain V of R is by integrating over this source charge distribution as described in section 5.13. This method is awkward in the presence of material interface which impose boundary conditions on the solution that must be satisfied simultaneously. For example, the electric potential on a perfectly conducting surface is constant, a constraint which is not taken into account in any of the experience. This fact is probably already known to the reader from past study of elementary circuit theory. However, this is established in the context of electromagnetics. So, in this section, we develop an alternating approach to calculating V of R that is accommodates these boundary conditions and thereby facilitates the analysis of the scalar potential field in the vicinity of structure and spectrality varying material properties. This alternating approach is based on Poisson's equation, which we now derive. We begin with the differential equation form of Gauss law, grad of D equal to PV, using the relationship D equal to E and keeping in mind our standard assumptions about material properties summarized. We obtain grad of E equal to PV by mu. Next, we apply the relationship E equal to minus grad of V, yielding grad dot grad V equal to minus PV by mu. This is a Poisson equation, but it is not in the form in which it is commonly employed. To obtain the alternative form, consider the operation g- grad dot grad in Cartesian coordinates. Grad dot grad equal to rho by rho x of x plus rho by rho y of y plus rho by rho z of z into rho by rho x of x plus rho by rho y of y plus rho by rho z of z, that equal to rho square by rho x square plus rho square by rho y square plus rho z by rho square by rho z square equal to grad square. That is the operation grad dot grad is identically the Laplacian operator square. Furthermore, this is truly regardless of the coordinate system employed. Thus, we obtain the following form of Poisson's equation: grad square V equal to minus PV by mu. Poisson's equation states that the Laplacian of the electric potential field is equal to the volume charge density divided by the permittivity with a change of sign. Note that the Poisson's equation is a partial differential equation and therefore can be solved using well-known techniques already established for such equation. In fact, the Poisson equation is an inhomogeneous differential equation with the inhomogeneous part PV by mu representing the source of the field. In the presence of material structure identity, the relevant boundary conditions at the interface between materials and the tasks of finding V of R equal to reduce it to the purely mathematical task of solving the associated boundary value problem. This approach is particularly effective when one of the materials is a perfect conductor or can be modeled as such a material. This is because, as noted at the beginning of the section, the electric potential at all points on the surface of a perfect conductor must be equal, resulting in a particularly similar boundary condition. In many other applications, the charge responsible for the electric field lies outside the domain of the problem. That is, we have non-zero electric field, hence potential non-zero electric potential in a region that is free of charge. In this case, Poisson's equation simplifies to Laplace equation. Rho rho uh, grad square V equal to 0. Laplace equation states that the Laplacian of the electric field is 0 in the source-free region. Thank you.